When we train a protein encoder network, for example, for the self-supervised training task of predicting the type of masked tokens, we've seen that we can extract after training a single numerical vector that represents our protein. If we now want to make predictions for proteins, for example, if we want to predict some kind of protein property, we need an additional machine learning model where we can use the protein representations extracted from the trained encoder as the model input and train the model for the prediction task of interest. We have also seen that we can train a protein encoder in a supervised way for the prediction task of interest. In this case, we already have a full model that makes use of the protein representation that was generated by the transformer encoder and makes a prediction for the protein. So in principle, we do not need an additional machine learning model where we can use the protein representation that comes out of the transformer as the model input. However, typically you get higher model performance if you extract the protein representation from the protein encoder after model training and use it as the input for a separate machine learning model. In this video, we will look at a machine learning task or a machine learning model that can successfully solve this task, gradient boosting decision trees. We will not go very much into detail, but I will give you a broad picture of what gradient boosting models are and how you can fit these for prediction tasks. Currently, gradient boosting decision trees are the machine learning models that typically perform best on vector input data such as protein representations. In my experience, they also clearly outperform separately trained fully connected neural networks applied to protein representations, but this also might depend on the prediction task and type of representation. So what are gradient boosting decision tree models? We will look at how gradient boosting models work for regression tasks when using the Python package xgboost. We will start by looking at a trained model where we have all the trees that are part of the gradient boosting decision tree models. And later we will look at how these trees are actually built based on the training data. If we have an input vector x that has dimension d, we want to predict the target value y. The input vector can, for example, be a protein representation that we generated using a transformer network encoder. For all input vectors x, we make an initial prediction. This initial prediction is the average of all target values y in the training set, and in this example, the average is 0.5. Then we have our first tree that we want to use to predict the error that we make using this initial prediction. If we can successfully predict this error, we can simply add it to the initial prediction and get the value close to the true value. For example, if the true value that we would like to predict is 1.4 and our initial prediction is 0.5, we would like that the first tree predicts something like we are 0.9 below the target value. Then we can simply add this value to the initial prediction and get a much better prediction value. Each gradient boosting tree has a structure similar to the one that you see on this slide. In every node, you have a decision rule that tells you whether you should go to the right or to the left in the tree. For example, we always start at the top of the tree, and if the third entry of your input vector x is smaller than 0.5, you go left in the tree. Otherwise, you go to the right branch. Then we have again decision rules depending on the values in x until we're finally in the green leaves of the tree. During training, our aim is to build a tree that groups data points with similar prediction errors in the same leaves. Then we can take the mean of all those errors for all training data points that end up in the same leaf and use this value as the prediction of the error. For example, for all training data points that ended up in the leaf C1, the average distance from the true value using the initial prediction value of 0.5 is minus 1.2. So for all these data points, it makes sense to move the prediction in the direction of minus 1.2. And we can achieve this by adding this value to the initial prediction of 0.5. However, we do not simply add this value to 0.5, but we first multiply it with a value smaller than 1, which is the learning rate of the gradient boosting model. Let's look at an example where we have chosen the learning rate to be equal to 0.3 and where we end up in the first leaf C1 for our input vector x. We would then calculate 0.5, which is our initial prediction, to 0.3, which is the learning rate, times the predicted error, which is minus 1.2. However, after doing this for all data points, the predictions for most data points will probably not be very accurate yet. So during training, again, for all training data points, it was calculated what the current prediction error is using the initial value in the first tree, and then a second tree was built that tries to predict the remaining error in the same way as discussed for tree number 1. For the second tree, we can again calculate for our input vector x, where we end up in the tree leaves. Let's assume in our example we are in leaf C3. This means we would multiply the value minus 0.3 times the learning rate and add it to our previous prediction. We would repeat this procedure until we reach the maximum number of trees that have been built during the training process. So we see that our gradient boosting model is an ensemble consisting of many decision trees that together try to predict the correct outcome. On the previous slide, we saw how we can make predictions once we have an already trained gradient boosting model. But how can we use the training data to build decision trees and decide which decision rules we have in the nodes of the tree? We will look at this using a very simple example. Let's say we only have 4 training data points and 2 input features, which means that the dimension of the input vector d is equal to 2. Now let's assume that we want to predict the optimal pH values for proteins based on these 2 input features. We can plot each of the 2 input features against the optimal pH values we want to predict. I've given each of the 4 training data points a different color. So for example, the first data point, our blue protein, has an input feature x1 equal to 1 and an input feature x2 equal to 3 and an optimal pH value of 7. And then you can see that we have 3 additional training data points represented by different colors. Based on these 4 training data points, we want to build a gradient boosting decision tree model to predict the optimal pH of proteins based on the input features x1 and x2. We have already seen on the previous slide that we make an initial prediction that is equal to the average of the target value of all training data points. So in our case, we calculate the average of the values 7, 5, 6, and 8, which is equal to 6.5. This is our initial prediction for all data points. We can now calculate for each data point how wrong we are using this prediction. Let's put all the prediction errors in a table. We now want to build a decision tree that predicts these errors for our data points. We saw on the previous slide that we want to find decision rules of the following style. We want to look at an entry of the input vector x, and based on whether this entry is greater or less than a chosen value, we split our dataset in 2 groups. We want to find decision rules that split the dataset in such a way that we have similar prediction errors in the resulting groups. Now we need to quantify what we mean by similar. We need a rule to decide how to best split the model into 2 groups. For each new group of data points, we can calculate their similarity score. And we want the similarity scores to be as high as possible. Here you can see the formula for the similarity score. We sum up all the prediction errors and then we square the sum and divide by the number of data points. For example, let's calculate the similarity score before we split the data set. We call this the root similarity score because we always have all the data points in the root of each tree. You can see that the errors of all the data points cancel each other out because we have a very or because we have very dissimilar errors that are positive and negative, and therefore we get a similarity score of 0. Okay, let's do a quick summary. We defined the similarity score and calculated it for the current prediction errors of the whole data set, which is 0. Now we want to formally define what we want to achieve. We want to find a decision rule, which will be part of our decision tree, that divides the data set into a left group in the tree and a right group, where we achieve a high similarity score for both subgroups. More precisely, we want to find or we want to choose the input feature I and the threshold A that gives the biggest gain. To find this, we test all possible combinations of I and A. In our case, this would mean we would set I to the values of 1 and 2, since we have two different input features, and we would test all values A that split the dataset into two groups. In our case, we would test a value between 1 and 2, a value between 2 and 3, and a value between 3 and 4. You can see that choosing values larger than 4 or smaller than 1 doesn't make any sense, because then we would have all data points in one subgroup and no data points in the other subgroup. After we tested all possible ways of splitting our dataset in this way, we select the rule that gives us the biggest gain. In our case, this is the following rule. All data points where x1 is less than 4 go into the left bucket, and all other data points go into the right bucket. This results in a similarity score gain of 3. And you can test for yourself that you cannot find a decision rule that leads to a higher gain. And since we have several data points in the left branch of the tree, we can try again to split this subset by adding a decision rule. Splitting the left branch again results in the tree that you see here. We see that the splitting makes sense since the red and green protein have a negative prediction error and the blue protein has a positive prediction error. So it's good that we are able to split these again. If we assume for simplicity that we have a maximum number of tree depth of 2, we have finished with building this tree. Now we can look at the new predictions we get using this decision tree. Let's say the learning rate is 0.5. Then you can see how we can calculate the new predictions, and you can see that our predictions are actually getting better. Now we can repeat this by building a decision tree in exactly the same way, but this time we try to predict our new prediction errors. But I will not go through this process, since this works in exactly the same way as you have seen for the tree that we've just discussed. This was, of course, only a very simple and small example of how we can build gradient boosting decision trees using our training data, and we left out a lot of details, but I hope this gives you a rough understanding of what happens during the training process. Now we want to look at the most important hyperparameters that we can tune when adjusting gradient boosting models when using the Python package xgboost. When fitting a gradient boosting models, we typically split our dataset in a training, validation, and test set. We then search for the best set of hyperparameters that lead to the best results on the validation set while training the model on the training set, since selecting the hyperparameters such that we get the best results on the validation set. This leads to a little bit of overfitting on the validation set, and we have our test set to evaluate the true model performance for the final model on this independent test set. The hyperparameter names that you will see on the slides are identical to the names in the XGBoost package. The first one is the learning rate, and you have already seen it on the previous slides. The learning rate defines how much weight each new tree should get, or more specifically, we multiply the prediction of each tree with this number before adding it to the overall prediction. This value can range between 0 and 1, where values close to 0 mean that each new prediction gets a very low weight, and the default value in XGBoost is 0.3. The next hyperparameters we are looking at are the regularization coefficients lambda and alpha, that on the one hand penalize large predictions in the leaves and On the other hand, lower the influence of branches where we only have very few training data points. We have seen in our example that we can get branches where we only have one training data point, and it is easy for this branch to get a very high similarity score because we do not compare the error of this data point with any other data point. So it's good to weaken the influence of branches that would only contain very few data points. Another very important hyperparameter is the maximum depth of a tree. This defines how often we are allowed to split the dataset using the decision rules until we are in the leaves and make predictions. In our examples on the previous slides, we had for simplicity a maximum tree depth of only 2, but in practice this value is typically much higher. Increasing this value will make the model more complex, but it is also more likely to overfit to your training data. In XGBoost, the default value is 6, and this variable can take any positive integer. And if you set this number to 0, you do not constrain the depth of the tree at all. Another very important hyperparameter is n estimators, which specifies how many trees will be part of the gradient boosting decision tree model. This variable can take any positive integer as a value. In practice, for large datasets with high dimensional input features, it can be best to set this number to a few hundred or even a few thousand. The last hyperparameter we are looking at is minimum child weight. This parameter tells the model when to stop splitting nodes, even though the maximum depth of the tree might not yet be reached. For regression tasks, this number simply tells the model to stop if the number of data points in a node falls below this threshold. For example, if we set this value to 5, we only have 5 data points in a node, we would not further split this node. For binary classification tasks, the interpretation is not the same, but it basically tells the model to stop splitting if the classes in a node become too imbalanced. For example, if we have mostly data points that belong to the positive class and only very few data points that belong to the negative class, the model would stop splitting if this imbalance is too high. This can be helpful because it prevents the model from creating overly specific rules that only apply to a very small number of cases, thus avoiding overfitting. And these were only the most important hyperparameters of a XGBoost model, but if you're interested in additional parameters that can be adjusted, you can read about these, for example, in the XGBoost documentation. So far, we have seen how gradient boosting decision tree models work for regression tasks. On this slide, I will quickly talk about how gradient boosting works for binary classification tasks, where we want to predict for each data point either the positive class, typically represented by a 1, or the negative class, typically represented by a 0. We will not go very much into the details, but we will see that the overall process is very similar. If we fit a gradient boosting model for binary classification task, the predicted output value will not be simply the positive or the negative class, but a score between 0 and 1. We can interpret the score as a probability of the data point belonging to the positive class. For example, a score of 0.7 could be interpreted as the model thinks there is a 70% chance that this data point belongs to the positive class. And hence, typically all data points with predicted scores above 0.5 would be classified as positive, and all data points with values of 0.5 or lower are negative. Similar as for the regression prediction task, when we build a new tree during the training process, with this new tree, we want to predict the errors that we have made so far with all the existing trees. The error that we're predicting is defined as the difference between the true class label, which is either equal to 1 or to 0, and the predicted score, which is, as we have seen, a value between 0 and 1. We then try to build a new decision rule with which we try to predict these prediction errors. And then we add this prediction to our current prediction in the hope of improving the overall prediction. As you can see, the overall concept is very similar to the process for the regression tasks. What is slightly different is how we calculate the similarity score based on which we split the nodes in a tree. However, the decision rules are still the same. We look at a single entry of the input features and split the dataset based on whether this feature is smaller or larger than a specific threshold. And the idea of the similarity score is also the same. We want to find rules that split our dataset such that we have more similar errors in the same branches. Another thing that is a little bit different, but where in principle the idea is very similar, is how we calculate the predictions in the leaves. For the regression task, we've seen that we can simply calculate the mean of all the prediction errors of all data points that ended in the same leaf. For binary classification, we do something similar, but we do not simply calculate the sum of all errors and divide by the number of data points, but we divide by something that is weighted based on the previous prediction values for all data points in this leaf. But as I said, the general idea is very similar to what we have seen before. When fitting a gradient boosting model for a binary classification task, we've seen on the previous slide that we want to obtain a score between 0 and 1 that we can interpret as a probability. However, the model does not directly predict this probability score between 0 and 1, but instead it predicts a log of the odds score, which we call S. The odds are defined as the likelihood of the positive class divided by the likelihood of the negative class, which is p divided by 1 minus p if p is the probability for the positive class. We can convert this log of the odds score into a probability score by applying the logistic function that is also known as the sigmoid function, which results in a value that is between 0 and 1 that we can interpret as a probability of the data point belonging to the positive class. As for the regression task, we start our gradient boosting model by making the same initial prediction for all data points in the dataset. For the regression task, we calculated the average of the target value for all training data points. Here we calculate the log of the odds for the training data points. This means we calculate the number of positive data points and divide these by the number of data points with negative class labels in the training set. As we have seen on the previous slide, we can calculate how good or bad we're doing by calculating the prediction error that is defined as the true class label, which is either 0 or 1, and the predicted probability of the gradient boosting model, which we get by converting the predicted log of the odds score into a probability score. As for the regression task, we now want to minimize these prediction errors for all training data points by building a new gradient boosting decision tree. To achieve this, we split the dataset using decision rules and decision trees as we've seen before by splitting the dataset in such a way that we achieve data points with similar prediction errors in the leaves of the tree. However, for calculating a prediction value for all data points that ended up in the same leaf, we do not simply calculate the average of all prediction errors as we've done before, but instead we want to obtain log of the odds predictions and we use the following formula. We sum all errors of the training data points that end up in the same leaf, and then we do not simply divide by the number of data points, but we calculate the sum of the predicted probability for a certain data point times 1 minus the predicted probability. You can see the plot of the probability times 1 minus the probability here on the right, and you can see that we get larger values for probabilities closer to 0.5 and smaller values for probabilities close to 0 and 1. I'm not going to derive here why we use exactly this function, but this is the formula that you get when you try to minimize the binary cross entropy, a loss function for binary classification tasks, for all data points that end up in this leaf. We use the result of this function, and as before for the regression task, we multiply it with the learning rate and we add the result of the previous log of the odds prediction score, which gives us our new log of the odds prediction score. Finally, we will have a look at a very simple example of how we can implement the training of a gradient boosting decision tree model in Python using the xgboost package. We are first loading the xgboost package and NumPy, which we need to define the input matrices. And you can see here that I use version 2.03 of xgboost. Here we want to copy our very simple regression example that we have looked at the beginning of this video, where we had 4 different training data points, each representing a protein for which we want to predict its optimal pH value. We define the input and the output values for this task. You can see that exactly as in the example, here we have 2 input values for each data point and 1 target value. Next, we define our gradient boosting model with xgboost regressor. We get a gradient boosting model for a regression prediction task, and we store this model in the variable named model. In the variable objective, we define that we want to optimize this to minimize the mean squared error during training. And then you can see that we define a few hyperparameters that we already discussed. We set the learning rate to 0.5, the maximum depth of tree is set to 2, and estimators defines that we only want to build 2 trees, and we set the regularization coefficients to 0. We can then fit this model based on our training data using model.fit. Then we can get predictions using model.predict. Here we apply this function to our training data, whereas typically we would first split the data into training and validation data, fit the model on the training data, and then validate the model only on the validation data that we have not used for model training. And you can see that on this very simple data set, we get with this model predictions that are close to the true actual values. The xgboost package also gives us the option to plot the trees that are part of the trained gradient boosting model. So let's have a look at the 2 fitted trees from the example of the previous slide. Here you can see the first tree. In this tree, you can see f0, which corresponds to the first input feature. Earlier in this video, we named this variable x1. If you compare this tree to the tree from our earlier example, you can see that the trees are identical, with the only exception that the values in the leaves are only half of the values that we had earlier. The reason for that is that we have set the learning rate in this model to 0.5. And if you remember, we multiply the predicted values of each tree by 0.5. So this is what happened here. The values in the leaf are directly multiplied by the learning rate. You can set the learning rate to 1, and then you see that we get exactly the same values from our earlier example. For completeness, here's also the second tree of our gradient boosting model, and you can see that this tree now also includes the second input feature f1, which corresponds to x2 in our earlier example.